Welcome back to the Explainer. Today we are looking into the high-stakes, entirely invisible mechanics that literally keep massive offshore power grids alive. If you've ever wondered how an isolated oil platform out in the middle of the ocean prevents a complete catastrophic blackout when a sudden immense electrical load hits the system, well, you are in the exact right place. All right, let's dive into this. I want you to picture yourself standing on the deck of an offshore platform in the Gulf of Mexico. It's 2 a.m., the air is thick with 100% humidity, and right beneath your feet, the deck is physically vibrating. That vibration? That's a massive gas turbine running at 3,000 RPM. It is the absolute heart of the offshore power system. Out there, you're completely isolated. You're relying entirely on your own gas turbine-driven generators to produce every single watt of electricity on board. Here's our quick roadmap for today's Explainer. The offshore grid, the motor start problem, Droop governing defined, the Droop equation, and finally, sharing the load. Section 1. The offshore power grid. Out on the water, a self-contained island mode power grid is incredibly delicate. Unlike onshore grids that are backed up by massive interconnected utility networks, these offshore grids have literally zero margin for error. A sudden disturbance out here, it doesn't just make the lights flicker, it risks a cascade tripping of the gas turbines. And that means a total platform shutdown and a massive loss of production. So, understanding this machine is not optional. Every single watt of electricity pumping through that platform depends on a perfectly balanced mechanical turbine. The physical power output of the turbine has to exactly match the electrical power being consumed at every single millisecond. If demand changes, that machine must react instantly. Which brings us to a rather intense question. What actually happens to a power grid when a massive 10-megawatt motor just suddenly turns on? Because in offshore operations, operators actually have to do this a lot. They need to start huge loads, like massive export compressors or water injection pumps, directly on the line. Section 2. The motor start problem. Let's see how this physical crisis unfolds inside the generator. When that massive load hits, the starting current for those big induction motors is just absolutely huge. It creates an immediate, violent demand for electrical power that the mechanical turbine simply hasn't prepared for yet. It's exactly like driving a car on cruise control and suddenly hitting a massive steep hill. First, the large motor starts. This sudden, heavy electrical load causes the generator shaft to physically slow down for a second. And because that spinning shaft speed dictates our electrical frequency, the frequency dips right below the standard 50 Hz. Next, the system's governor detects this drop and instantly injects more fuel into the turbine. Finally, the system recovers. If we were looking at a graph of frequency over time right now, we'd see a totally flat line at 50 Hz, then a sharp dip the second the motor starts, followed by the governor's response, and a smooth recovery curve right back to stability. Section 3. What is droop governing? To prevent a total platform blackout during that scary frequency dip, we rely on the true mechanical hero of our story, the closed-loop speed governor. All prime movers used for driving electrical generators are equipped with these governors. They detect that speed deviation and essentially save the day. And this brings us to our formal definition. Droop governing is a form of proportional control where a fall in shaft speed, and therefore generator frequency, occurs as the electrical load is increased. Now, the brilliant part of this engineering is that this drop in frequency isn't a flaw. It's entirely intentional. The system intentionally allows the frequency to droop just enough to create the steady-state error needed to trigger that vital increase in fuel. To put a real number on this, it's customary for a tiny 4% droop to occur when a 100% electrical load is applied to a generator. So, on a standard power system, moving from zero load to absolute full load might only drop the frequency by a couple of hertz. But man, that incredibly small number does incredibly heavy lifting. It is the precise mathematical trigger keeping the entire generator balanced. Section 4. The Droop equation. Okay, so we've talked about the physical hardware, the fuel valves, the spinning shaft, but now let's zoom in on the specific mathematical formula that dictates this automated response. Because this isn't just a mechanical guessing game, right? It's pure, elegant math. If we look at the droop characteristic graph, plotted out with power output on the x-axis from 0 to 100%, and frequency on the y-axis going from roughly 50.5 down to 48.5 hertz, you get a straight line with a negative slope. As the power output requirement rises, the frequency falls in a perfectly predictable linear way.
Now, what's really interesting about this is how we express that exact sloping line. We use this formula. Droop, which we call pi, equals FZI minus F multiplied by GI divided by DI times F0. It looks like a mouthful, but this beautifully simple equation is the actual literal logic controlling the massive generator's behavior at any given second.
Let's deconstruct that equation piece by piece, so it's not just alphabet soup. Pi is the electrical load the generator takes on. This is determined by the difference between FYZ, which is our frequency set point, and F, the actual current system frequency. We multiply that difference by GI, the physical electrical rating of the generator, over the droop setting DI, times the nominal system frequency, F0. All it's doing is linking the physical machine limits directly with the real-time electrical demands.
Section 5, sharing the load.
Now let's expand the narrative a bit, because offshore platforms rarely rely on just one turbine. When you have multiple generators connected to the same bus bars, they use this exact same math to work together as a team. If you plotted two generators on our characteristic graph, you'd get two parallel lines. And exact where those two lines intersect the system's total load line, that is the exact point where they share the load. So the crucial point here is what happens during commissioning. If two generators have identical droop settings and identical power ratings, they share the load perfectly equally. It's a harmonious system. But if those settings are mismatched, you get unequal load sharing. One generator hogs all the load while the other slacks off, which severely risks cascade tripping and catastrophic overload. Ensuring those droop settings are perfectly matched during commissioning is absolutely critical. So what happens if operators do find themselves with unequal load sharing? Well, they have to fix it by physically shifting where those two droop lines intersect on the graph. They can do this by changing the specific speed setting, the set point, of generator 1 or generator 2, but ideally they change both simultaneously. By adjusting both set points together, they not only equalize the load sharing, but they pull the overall system frequency right back up to a perfect 100%, like a solid 60 Hz.
I know it can sound mathematically dense, but as our source material explicitly points out, Droop Governing provides the simplest method of sharing load between a group of generators connected to the same power system. By just letting the frequency sag a tiny bit naturally, these massive, intimidating machines literally self-regulate and balance each other out using fundamental physics.
Which leaves us with kind of a mind-blowing final thought. We rely on electricity for everything, right? We often just assume it's this static utility that magically appears out of the wall. But the next time you flick a switch, will you think about the delicate, invisible mathematical balance, the spinning turbines, the calculated frequency dips, the automated mechanical governors, working furiously behind the scenes to keep the lights on? Thank you for joining me for this explainer, and as always, keep learning.